So what I'm going to do for a minimum amount of listening to me today is tell you how to enter your own data into HydroLight, and then kind of do a run and show you a couple of examples of that. And you only missed 10 seconds worth, so no loss. Anyway, I'll show you how it works, and then you guys can carry on with your homework problems that I'll give you. So the bottom line is this: any kind of data that you would have that you want to read into HydroLight has a HydroLight standard format. So this could be chlorophyll concentration profile, AC9 data, sky irradiance data, bottom reflectance data, mineral concentration data, whatever it is. So I'll just show you how those data files work. Then when you go get some AC9 data next week, you process your data, clean it all up, bin it, smooth it, throw out the bad values, and then put it on this HydroLight standard format, and then HydroLight can then read that file and use your AC9 data. So I'll just go here and show you there's examples of all of these files. So if we go to, let's see, HE52 student version for Maine. Okay, so if we look in the data directory, for example, defaults, so there's, let's see, that's not the one I wanted. Let's back up one. Examples, I guess. Yeah. Okay, so let's say you have a chlorophyll profile. So here's a file named chlorophyll Z data. So if we just open that guy up and take a look at what's there. And would you rather have the lights on or off? Does it matter? Okay, as long as you can see it. Okay, so the way these standard format files work is there's always 10 records that you can use to identify your data. And the next version is a little more general, but the version you have to have exactly 10 lines here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then your data starts, whatever kind it is, as the 11th record. Okay, so in this case, this is a file of chlorophyll data, and that's going to simply be pairs of this is A star chlorophyll. Okay, well, we'll go with that. So I thought it was chlorophyll Z. I just clicked the wrong file name. So this is an A star of chlorophyll lambda file. So we just have pairs of wavelength and A star, which is units of meters squared per gram. And I realize now I've had like 100 people ask me what's mg. Well, that's milligrams, but I know what it was. I used to have a GM there, and GM's the old abbreviation for gram. That's what it was. Anyway, so the A star is meters squared per milligram of chlorophyll, because remember, this thing, which is meters squared per milligram, is going to get multiplied by a chlorophyll concentration, which is milligrams per cubic meter, and then that's going to give me an absorption coefficient in 1 over meters, which is what you have to have for absorption. So anyway, it's just pairs of wavelength and this value. So if you've taken your water sample, you've worked your magic on it in a spectrophotometer, whatever, you've got your own spectrum for your favorite phytoplankton, normalized by the chlorophyll. All you have to do is take this file, you can put your own documentation up there, and then throw out these values and put in your values. And then, save it with a different file name. And then if you go down to the bottom here, it eventually, I have data through 800 nanometers. if it's just the end of file, then it'll say, fine, I hit an end of file, I'm done. The danger is if you have a blank line after that last real record, HydroLight will read the blank line as zeros, and it'll say, oh, I've gone from wavelength 800 to wavelength 0, and it'll print some rude message about how the wavelengths have to be in order and stop. So the recommended way to end the data file is just put a record of like negative numbers here. So the wavelengths are always positive, so HydroLight will read along, it hits a negative wavelength, and it says, oh, okay, I'm done, don't read anymore. So that's the way you would set up a file for a concentration-specific absorption or scattering spectrum. For example, if we go back up here and click on the one I meant to click on, here's chlorophyll Z data. So once again, there's 10 records, and now it's pairs of depth and chlorophyll concentration in milligrams per cubic meter, and a record of -1s, because HydroLight knows the depth's always going to be positive, so it hits the negative guy and it stops. So you could, if you had a chlorophyll profile that you had either measured or made up, you'd just put in your depths, your chlorophyll values, save it as a new file name, you're done. Then let's take, here's an AC9 file. Okay, so, and this is real data in this case. There's my 10 records. Then it says record 11, which is the 10th header record, gives the number of wavelengths and the wavelengths. So it comes down, it says I've read my 10 header records. Oh, this file has 9 wavelengths, and here are the wavelengths, 412, 440, etc. Your AC9 might have slightly different wavelengths. And then there's just, this is the first depth, the second depth, etc. Here's A at 412, A at 440, 488, da-da-da-da-da. If we go out to the right here, there's wherever it went, whoops, yeah, A at 715, it's zeros, because this particular data file, they did the scattering correction where they just set A at 715 to 0. And so these values have had pure water removed. And then that actually should say C at 412. So then there were the 9 absorptions, and now there's the 9 beam attenuations on out to the end there. And so there's a record like that for...
That's a typo, right? After A715, there's A412.
Yeah, as I said, that should be C412 there. So I've only been using this file for like 22 years before I noticed that. And let's save this guy now.
Can you bring the columns? Is that spaces or tabs?
It's spaces. You probably get away with tabs, maybe, but Fortran doesn't like tabs. So if you have, the real evil comes like you've got this on an Excel spreadsheet. So you can kind of block out this data and save it as a text file, but I always then go in and convert tabs to like 3 spaces. Or you can't have a comma separated thing like some things do. So these are, 3 or 4 simply blanks between the numbers. They're not tabs. And sometimes, I'll try a file and it might be tabs, and Fortran will read it fine, and the next time it'll some way try to read the tab as a number, so just weird things happen. Anyway, then you go down, and I finally had a record there where there was a negative depth, and I just usually copy this last line, paste it in, change the depth to negative, doesn't matter what those numbers are because they're not going to be used. So that's the HydroLight standard format for AC9, ACS, whatever. A bit of warning, if you have an ACS, okay, so this line is going to say, how many wavelengths do they have? 100 and what? for an ACS. It's like 116 wavelengths or something. So this would be like 116, and then all of those wavelengths listed across there. Now the AC9, you have exactly the same wavelengths for the A and the C. With the ACS, you have the same number of wavelengths, but the particular wavelengths may not be the same. So HydroLight's going to read this and say, oh, you know, the third wavelength is 488, and so there it is, and then the third C it's going to interpret as 488. With ACS data, before you get to this stage, you've cleaned it all up, spline fit it to a common set of wavelengths for the A and for the C. And you know, maybe you do like every 5 nanometers or every 10 or whatever you want, but just make sure that your A and your C values are referring to the same set of wavelengths. Okay, so that's that. Then there's, well, let's just look at the filtered one here. So you've got, the other one was the total, this is the filtered, same format, so here's the absorptions, and then you look out to the right, and somewhere here, let's see, okay, so here's the filtered A, and then I guess it's the C from the, I'm trying to remember how that worked. But anyway, in this case, it's only going to use the absorptions because this is, you know, in theory, the scattering for CDOM is 0. So if you give it a file and it says, this is data from a filtered AC9, it knows, go ahead and read it all, but you're only going to use the absorptions for the CDOM part of the calculation. Yeah.
We still have to put the C data.
The C's still have to be there, yeah. I'm pretty sure it reads them. Okay, well, let's say here's, suppose you have a Hydroscat 6, and here's its data. Same format, you know, the 10 records. Here now it says there's 6 wavelengths. Here they are. Here's the first depth. Here's the 6 backscatter values. Now, the standard for AC9 ACS data is that you have removed the chlorophyll. Removed the water contribution. For backscatter, some people remove water, some people don't. So when you run the front end and you say, okay, I'm going to read in this file of backscatter data, there's a little button to click that says I have or I have not removed the pure water contribution. And if you have, HydroLight will put it back in. If you haven't, it'll use the numbers as they are. For the AC9 or ACS data, HydroLight is always going to add the water back in. Okay, let's see, what else? You know, there's other things. Well, of course, like a mineral concentration works just like a chlorophyll. It's just minerals instead of chlorophyll. Here's, you know, irradiance data, and there's, let's take a look at this one. There's several ways you can read in sky irradiance data. So this is a format where it's a wavelength, the direct contribution, and the diffuse contribution. So that may be what you're getting out of your instrument. There's another format where you can read in the direct and the total, or you can read in the total and the ratio of direct to total. So there's a bunch of different ways you can do that, and then when you read the file in, you click which one of these things it is. And also, don't just leave blank lines in here because you'll miscount them, and then you'll have like 11 blank lines, and then HydroLight wants to read the 11th one as the first data record. So at least just put numbers 1 through 10 if you don't really want to document your file. Okay, so I think enough said on those kinds of things. So now let's fire up HydroLight here and just do a run with this. And I know some of you have already been playing with the Case 2 model and stuff. So this is, let's say, Thursday, run 1. Okay. And I'll just call this, whoops, what have I done here? Case 2 example. Okay. So let's say we're going to read in our own data. Okay, there's one of the IOP options that says measured IOPs. I have IOPs obtained from standard format, user supplied, AC, and optionally BB files. So let's pick that guy. And it comes down and says, okay, we're going to have pure water is component 1. Component 2 is everything else, whatever was in the water that you measured with your AC9. And then component 3, if present, is CDOM obtained from an additional filtered AC instrument. This is used only for CDOM fluorescence. The bottom line here is the only reason HydroLight needs to know how much of the total absorption is due to CDOM is if you include CDOM fluorescence. So it then needs to know how much is absorbed by CDOM, or if you need to know if you want chlorophyll fluorescence, you need to know how much of the light is absorbed by chlorophyll as opposed to all the other stuff. So if you don't include fluorescence, you don't need that file. If you have it, fine, but you just kind of have to think about what's really going on here. Okay, so yeah, we're going to do, let's use Pope and Fry's pure seawater things. That's cool. Then we come down and it says, okay, what's the name of your data file? Well, I'm going to browse off and to wherever I've stored this, and I should fire up here before I do that. When you look in the data directory, there's directories here that have bottom reflectance files, my defaults, phase functions, etc. And there's one called user. So I strongly suggest if you have data files, put them in the user directory, or you can make a subdirectory under there, whatever you want to do. Then you don't mix your data files up with the ones that come with HydroLight. Minor point, but just good to keep things separate. Okay, so it says, let's see, I'm supposed to be reading in an AC9 file here, is that it? Yeah, so I go browse off to wherever, let's just go to this examples thing, and I will pick my AC9 file. Now you might go to the user directory, Tuesday Cruise, whatever, and pick your AC9 file. Then we now are going to get A and B from that, but we still have to pick a phase function. So maybe I have my own phase function, I fixed it up, I've got a file name, I can add it to here. We won't do that in here. You can use a Fournier-Ferrand phase function that's got a constant BB over B value, so all depths and all wavelengths. You can use one that has a BB over B value specified by a power law. So if we look at that, there's a little model here that basically says backscatter fraction equals the value at a reference wavelength and then a lambda to the minus m kind of dependence. And you can put in, let's say it's 1% and it's lambda over 550 to the minus 0.5 or 0.5, whatever you want. So you can play with that. Let's back up here. Okay, so I browsed from my file, or I could, maybe I have it says here, get that out of the way. I'm going to use a Fournier-Ferrand phase function with a variable backscatter fraction using B from the ASC9 file and BB from some standard format BB file, which could be from a BB9, a HydroScat6, or whatever. So you could browse for that file. And then it says if you have that, the BB data file either includes pure water backscatter or doesn't. So just pick whichever one it is. Usually it won't really matter, but in very clear water it does. So let's just say for the chlorophyll, I'm going to use a Fournier-Ferrand with, let's say it's going to be 1% and then lambda to the minus 0.5, just to have some numbers. Okay, so then we go to the next page. Do I want to include chlorophyll fluorescence, blah, blah, blah. Let's say I want to include chlorophyll fluorescence. Then it comes up and says, well, wait a minute. You read in an AC9 file. You haven't told me anything about the chlorophyll. And then you say, well, I didn't measure chlorophyll because I had an AC9, so I measured the total IOPs. Well, got to remember, if you need to include chlorophyll fluorescence, even though that IOP is included in the AC9 data, you still have to know how much chlorophyll was there in order for HydroLight to figure out how much of the total absorption was being absorbed by chlorophyll. So you could say, oh, okay, I did measure the chlorophyll profile, and so I will go get that, and there's the chlorophyll Z data, and presumably this, of course, goes with your AC9 data. These two files are, not compatible, but they'll still put out numbers. And so now I know the chlorophyll concentration, and now I have to figure out, well, how do I turn that into specific absorption? Well, if you're doing great work, you took this data, you measured the chlorophyll specific absorption spectrum here, you have a file with these numbers, you put it on the format, you read that file in. Or maybe you say, well, I didn't do all of that. All I measured was the chlorophyll concentrations, so I'll just use this nice little formula here for case 1 water and, hope for the best. But better that you've measured your own, you have your own spectrum, then you're good to go. Then it says, okay, I'm going to get the concentration information from this file, and let's see, will be read from the user supplied data file by this subroutine that reads concentration data. So yeah, okay, that looks like what I wanted. And then it's going to read, yeah, okay, and then it says run must include relevant excitation and emission wavelengths. Well, remember, if we're interested in chlorophyll fluorescence, we better start back at 400, otherwise you're missing part of the fluoresced light. Okay, wavelength selection, once again, that's all just like before. And and notice, of course, there's no option to pick a single wavelength run because we've said there's fluorescence. So you pick whatever you want here. I'll just use that for the moment. Then, this stuff is the same as you've seen before. Maybe you actually do have, let's say we put the sun at 50 degrees, and maybe it's an overcast day like it was the other day. So we're going to have 100% overcast sky. And if the Monday lab, when Ken was doing the radiometry, if that's not proof of living a pious, virtuous life, I don't know what is, because it was cloudy all morning, came time for the lab, it cleared off, we got the data, and then the clouds came back for the rest of the day. That never would have happened for me. For Ken, yes, but not for me. So anyway, we're going to model a heavily overcast sky here, just for the heck of it. And yeah, we'll just play like it's annual average. We'll call the rad trend model, fine, use all of that. And it's finite depth, and we're going to have the bottom depend on wavelength, And if you have your own measured bottom reflectance for the mud out here, you put that on a standard format file. You can actually add that file to the little pull down list here. I won't bother to show you how to do that, but you would then go in and get your file here out of this list. And then same thing here, we'll do a run down to, 15 meters by 5 and, save that input, well, whatever, and we do the run. So let's just get that out of the way. Okay, so that's the story on putting in your own data files. Now I'll go back and do just one more little example of saying I want to model case 2 water. So in your version, there's this sort of generic case 2 IOP model, and let's just see how that works. It's going to have 4 components: pure water, chlorophyll-bearing particles, CDOM that does not covary with chlorophyll, and mineral particles that do not covary with chlorophyll. So, we'll keep the seawater thing. Okay, where do we get the chlorophyll? Oh, I don't know. Let's just say it's constant for simplicity here. And I'll say the chlorophyll. What's the chlorophyll in the Damariscotta River? About 5 or something? What kind of numbers were you guys getting? How much? 3? Okay. I established my reputation in one of the Friday Harbor classes when Mary Jane Perry asked the class, they said, look at this water here. Tell me what the chlorophyll is. And everybody's like, I don't know, it's like 3, it's 4 or something. Well, I have no clue about even what units chlorophyll is measured in. So I just said, 5.6. And they measured it, and it was like 5.65. Everybody thought, man, this guy's really good. I had no clue. Now I have a little better option. I would have guessed it out here. It was maybe 5, but okay, it's 3. So we have to pick how we're going to model this. So let's just use the sort of generic A-star chlorophyll spectrum. Fine. Scattering. Okay, there's a bunch of ways you can do it. The best one is you've taken your sample and you've actually measured a chlorophyll-specific scattering spectrum, which most people don't use or don't do. So maybe they use a power law, and let's say this is open ocean, and we're going to do remote sensing reflectance calculations. So we're going to pick these parameter values that are based on near-surface data recommended for remote sensing applications from Loisel and Morel. And we'll use that for beam C, because remember, these power laws give a better fit to beam C than they do to B, but if you want to use it for B, you can. So now we've defined how it's going to turn chlorophyll into a scattering coefficient. So here it's going to be 0.407, yeah. Question? Okay, it's going to be basically 0.407 times chlorophyll to the 0.795 and lambda over lambda naught to the wherever m went here somewhere. It's under there. So to the -1. Okay, so that's their best fit model. Okay, at any rate, we're turning chlorophyll into a scattering coefficient. Then we still have to pick a phase function. So I'm just, for simplicity, going to use this. So it's 1%. Cool. Then it goes on to CDOM. So what do you want to do for CDOM? Well, the best thing is you've got some measurement of CDOM at a reference wavelength, or you've written your own subroutine, which we're not going to do here. Or you could just say, well, I'll let CDOM be proportional to the chlorophyll, like in case 1 water, but maybe I'll want to change the parameter values. So maybe I think I have a little extra CDOM, so I'll pick this one. And then instead of letting the CDOM contribution be 20% of the chlorophyll at 440. With this exponent, I want it to be 30% because I think I have extra CDOM here, and I think my wavelength dependence is 0.017 instead of 0.014. Okay, whatever. We've now defined the CDOM. It's non-scattering. And now we have to put in the minerals. Well, I've done all the effort. I've taken the water and filtered it and got rid of the chlorophyll and whatever, and now I have a mineral concentration profile. And so I'm going to read in that concentration. So I go back to somewhere here. There's, whoops. Okay, there's some defaults. And I've determined that the mineral particles out here are brown earth, and so I'll use that file. That's a concentration. I got the wrong file there. That will blow up. So I've got, examples. So I have measured. Here's mineral Z data. So that's just some depth profile of mineral concentrations. And then I have to turn that concentration into A and B. So I come here and I say, oh, okay, I've looked at all this stuff under a microscope or whatever people do, and my mineral particles are, let's say, this brown earth stuff. Whoops. Wrong thing. I picked the B file. I need to get A star brown earth, and then that'll turn the concentration into an absorption coefficient for the minerals, and then I have to do the same thing for scattering, and I just want to make sure that I get the scattering, I get the file for brown earth scattering here. And then it can, once again, I can pick a power law, and maybe here I'll use these values and, hope for the best. Better that I've measured it, but I didn't really. And I still have to pick a phase function. So I think the mineral particles have, dang it. Okay. I accidentally hit the wrong button here. Okay, all that stuff's there still. I select a phase function specified. Well, I'm just going to use 3% here and go on. Okay, so now I've got all of that stuff defined.
I think you have to actually select it.
Did I mess something up?
I think you typed the value in, but the line wasn't.
Oh, okay. Usually it will not let you proceed if there's something that's not defined. Oh, yeah. Okay, continue.
No, it's still a construction.
Let's just go back here and just do this. So it's 3%. What the heck? Okay. Then let's just go ahead here and include all of these things. And it says now, here's where I'm going to get the chlorophyll. CDOM's going to covary. Be sure to include the right wavelengths. Okay, fine. And then same story for the rest of it. You go along. If you had that you want to read in your own irradiances that are coming off your deck cell. So there's three options. You go get your file. So let's just do that. Back up here. Let's see, is this, no, we want examples. And okay, so you had your deck cell and you came up with sky irradiances that were the direct and the diffuse. So those pairs we looked at. So you can say, I have direct and diffuse irradiances. That's what's in my file. So I will click that guy, and away we go. And we now have infinitely deep water and whatever else, and save all that data, and then we can do our HydroLight run. So that's sort of the way it works. And you can play around with that. The case 2 model doesn't have to be case 2 water. If you have AC9 or you have your own data, you put it on the files. If you get to the 4th form where it says what's the mineral concentration, you can just put in a 0 and it'll just have minerals will be in there, but the concentration's 0, so all their IOPs will be 0. So you can use the case 2 model to simulate case 1 water if you want to. Or if you put in 0 for chlorophyll and all you had in the water was minerals, you'd put in 0 for chlorophyll and the information for minerals, and the printout and stuff would still have chlorophyll, but the chlorophyll IOPs would be 0 if the concentration's 0. Okay, so enough said by me. Even I'm tired of listening to myself talk. So, and how I've stayed married for 38 years is kind of mysterious because my wife does not care anything about details. She wants to ask a question and the answer needs to be yes or no or 5. I want to then explain to her how you would start with quantum electrodynamics and then finally get to the answer of 5 an hour later. And so some way or another, it works for us. And I think it works because I disappear for like 6 weeks at a time to go teach classes in Maine, things like that. Okay, so first exercise today is just inputting your own chlorophyll of Z data. And you can take that chlorophyll Z data example, make up some numbers, do whatever you want, and just see how that works. And then there's one on inputting IOPs from AC and BB sensors. You kind of saw how that works. A couple of warnings that I've already given you are repeated here. Simulating case 2 waters, okay, we just saw that with the last models. Simulating optically shallow water, a bunch of you have already been running HydroLight with bottom reflectances. So you might even just make up some bottom reflectance with a step in it or something, play with it, see what happens. The best one though is providing HydroLight user support. Okay, real example. I got this, picture right here from somebody that says, well, I measured the green curve and HydroLight is putting out the red curve. So what's wrong with HydroLight? Well, at this point, I have no idea. So you've got to send me your data files. So she sends me her data files, and in less than 30 seconds, I solved the problem. So in the, somewhere in the HydroLight, the data user directory, there is a file. If we look at it here, so data, user, here's the AC9 Lab 2. There's the AC9 data file she sent me that's giving the bad, showing that HydroLight doesn't work. So run that through HydroLight and see if you can figure out what the problem is. If you can, John will probably hire you. And if you can't, well, then you're in the same boat she was in. 3, 4, 5. Okay, spread those around. 3, 4, 5, 6, 7. And 1, 2. All right, so, and then if you cook up some other weird thing, feel free to try it out, report on it tomorrow. You don't have to stick with just what's here. Everybody have one of these, or at least one's on the way. And, you know, I'll be around for the rest of the afternoon, and I'll hang around after dinner for further questions and see what happens.